All right. Now we can continue. Obviously, the trial of this short examination was not so successful, but that's something that we expected. I am still not sure about some further things. There's some chat inputs. Yeah, I can maybe upload to a web page as you suggest, and then link from there and input into the system, Canvas system. That's a good idea. In case it may be necessary. Yeah, thanks. But anyway, I'll make a few more trials. We have a lot of time still. Now let's continue with our discussion regarding the way to write down signals, to plot the signals. So it's critical to write the notation of a signal in continuous time versus discrete time. And it's also critical to plot those things. Now, I gave you one example of a proof question, but those exercises can be extended to the following questions. As exercises, where these questions are some the things that you may try by yourself. So the first question I asked, every function can be decomposed into its even and odd parts. Show that. The second question is an even signal times the same even signal. So it's a multiplication of two signals. How do we multiply two signals? Well, it's just like multiplying a sine with a cosine, for example, right? It's literally a term by term, time-wise multiplication. So if you multiply two even signals, you obtain, another even signal. So the multiplication of two even signals is an even signal. Time-wise, along the time axis multiplication. Another question, the multiplication of an even and an odd signal is an odd signal. I'm putting a hat on top of these x's to indicate that it's not the same x as the left-hand side, okay? It's a different function. I could say f, g, h, and things like that as the function names. It doesn't have to be x. And another thing to prove or show using the methods that I have discussed is the multiplication of two odd functions. The odd function with itself, in other words, will give you an even function, because they will be both negative or both positive. Their multiplications will always give you positive values, and they will be symmetric around the origin. Another thing, a symmetric integral from a point minus a to another point plus a, to the plus version of the same thing, of the integral of an odd function will be equal to 0, because an odd function is like an even function and folded backwards. So when you integrate, all the positive and negative terms will be encountered in this integration interval, which is also symmetric around origin. It's from minus a to a. So the integral will give you 0. Now these questions I'm giving you as examples because example questions because they are trivial. That was a term that I used in the short exam trial. I said solve the following trivial questions. Trivial means easy, obvious. There's nothing to solve. It is so obvious. These are also obvious and therefore trivial, but that also makes them a little bit difficult in terms of notation, because I'm not expecting you to write to the right of it if I ask you to prove it. If you say obvious, well, maybe in a scientific paper it may be okay because it is indeed obvious, but for a lecture it's not okay. I would ask from you to use one of those three techniques. to do this. And sometimes if it is too easy, you don't know how to do it. It is so obvious that, what am I going to do with it? You have to do something. You have to think of ways of making proofs. Now, an important topic, transformation of the independent variable, or let's say the time variable. The independent variable is the thing that appears inside the parentheses or square brackets. That is the independent variable. It's a time variable, and according to time variation, the function values change. So by saying a transformation of those, I'm talking about such transformations. Suppose you have an x of t, it may be given in the form of a plot. I can give you a plot of it. I can draw this function, or I can give some analytical ways of expressing it. Like I can say it's a rect function, rectangular function, or a triangular function, or a sine way. So the function I can write literally. But suppose x of t is given, the transformation is to x of minus t. For instance, this is a transformation of the independent variable. Clearly, we have already seen an example of this one. What do you need to do? You have to flip around the origin. For example, if this is x of t from 0 to 1 with the value 1, then x of minus t would become this. From minus 1 to 0 with the, again, a value. This is x of minus t. This is x of t. This is the first transformation of the independent variable, negating the time axis and therefore flipping around. Another transformation is from x of t or x of n. This time let's give it from a discrete example, because we have been doing continuous examples in too many times, so we will encounter them equally. So let's this time say x of n to x of n minus 3. What is it? It's a shift. I'm shifting the time index. But where is that shift towards? Is it towards right? If I say n minus 3, it's a shift by 3, obviously. But is it a shift to the right by an amount of 3? Or is it a shift to the left by an amount of 3? You know, many of the students, including myself, are sometimes unsure about that, and we get confused. Wait a minute. What kind of a thing are we talking about? I know the answer, by the way, but in case you are getting confused, think of it this way. Suppose that your signal is this, and all others are 0. So 0, minus 1, 2, 3. Oops, sorry, what? The time indices are incorrect. 0, 1, 2, 3, and it goes on, of course. Suppose this is x of n with values equaling to 3, 2, 1, and the others along the axis are 0. Suppose this is your discrete time function, x of n. What is x of n minus 3? How do we draw it? Assignment of specific points to the time axis may help you, because it does help me. For instance, in the new expression, if I say n is equal to 3, then it would correspond to x of 0. So at n is equal to 3, the thing that I would draw on the new function, which is this one, this function, corresponds to x0. So let me go to, this is 0, 1, 2, 3. Okay, 0, 1, 2, 3. And at 3, the value equals x of 0. What is x of 0? It is this. So obviously I have to draw this. Similarly, at n is equal to 4, it corresponds to x of 1, because 4 minus 3 is 1. And x of 1 is, as you see, this, 2. So at 4, This is 3, this is 2. And at 5, I will draw a 1. And at 6, again, it's 0 on the n-axis. So x of n minus 3, if I ask you to plot, you have to give me the right-hand side plot here. Obviously, if you say x of t minus, I don't know, some number, let's say capital T, causes a shift to the right by t, by an amount of t. Everything is shifted to the right. For example, if I say x of t minus 5, everything is shifted by 5 to the right-hand side. If it's discrete, the shift must be integers. But if it is a continuous time, if it is x of t, then the shift may be just any real value. I can say x of t minus pi, for example, which makes a shift by an amount of 3.14, etc. It's by pi, which is an irrational number. That's possible. If it is, however, for example, x of t plus 10, then it means it's a shift to the right by an amount of minus 10, which means shift to the left. So if it is x of t plus something, it means you are shifting your signal to the left by that amount. Now, another transformation we can talk about is this unfortunately only happens to continuous time. X of t is given to you, and from there you are trying to draw x of a minus t, where a is a real number. It can be an integer, but it doesn't have to be. It's just a real number. It can be greater than 1. It can be less than 1. So we have to think about two different cases. For example, x of 2t, where a is 2, right? For instance, suppose x of t is given to you like this, a triangle waveform. This is x of t on the t-axis. Outside the triangle is zeros. Can you plot x of 2t? Now again, sometimes it helps me to assign some numerical values to the axis and see where they really correspond to. For example, at t is equal to 0.5, I'm trying to draw this, okay, x of 2t on the t-axis. And this is 0.5, this is 1, this is minus 0.5, this is minus 1. What is x of 2t? How can we really draw this? What happens at 0.5 is interesting, for example, because 2 times 0.5 for x of 2t will give me x of 1. And x of 1 is here, this point. So this point actually appears at 0.5. It's here. That point is transformed to this point. When t is 0, 2t is also 0. So the 0 point is transformed to 0. X of 0 is at 0. And minus 0.5 times 2 is minus 1. So this point appears here in my new plot. And my new signal is therefore something like this. It's the same triangle which gets narrower. It shrinks in time domain. So the original was wider, x of t, and x of 2t is narrower. For example, if it is a sinusoid, x of t is a sinusoid, x of 2t will be a more frequently oscillating with a higher frequency or smaller period sinusoid. Okay, it shrinks, gets narrower in time domain if a is greater than 1. Conversely, if you say x of t over 3, then what does this look like? Just the opposite, of course. Now, when t is equal to 3, it makes x of 3 over 3, which is x of 1, which is this point. So essentially at 3, I have this point. And at -3, I have this point. And at 0, I have the 0 point. And this is the function that I have for x of t over 3. So if I multiply with something less than 1, or if I multiply with something, or if I divide by something greater than 1, in other words, then the signal becomes wider, right? Now, all the other transformations that you can think of in the independent variable in the along the time axis can be consisting of a mixture of these altogether. For example, x of t, this time I will give you something else. It is this half triangular shape from 0 to 1. It's a ramp function, increasing up to 1 and then coming back to 0 again, and that's it. 0 before and after. Before 0 and after 1. Now, the question may be, I'm just inventing here, is the new function y of t, which is equal to x of minus t plus 3 over 2. Look at that. I'm doing just all the nasty things all together. I am flipping around because there's a minus t. I am making some sort of shift because of this plus 3. And also, I am scaling the time by multiplying with 1 over 2. Or dividing by 2. And by the way, I also ask another question here. Z of t is equal to x of minus t over 2 plus 3. Okay, this is a different signal. It's clear, y of t is clearly different from z of t. Now your mission, you see, that's what we as professors or teachers do. We give trivial examples, like the above cases, and then instantly we ask, after these trivial questions, we ask some hard questions like this. This is question number 1, this is question number 2. But still, this is an example like a homework. I'm giving you this as a homework, but I'm not gonna evaluate. But if any of you guys fail to work on it and have an understanding about which one to apply first, do we first negate and then shift, or first scale and then shift and then negate? They all correspond to different things. And as you may guess, I don't know which one to do first. I get easily confused with these kind of independent variable alterations. But you have to find a way to do it. And these are the homework questions, which are level 2 questions. Level 1 was the trivial questions here. Level 2 are these, abruptly becoming indefinitely more difficult. And the exam questions will be level 3 questions, which are indefinitely more difficult than even this one. So you have to be careful about understanding the topic and applying it. You see, understanding here, easy, piece of cake, trivial. Applying, immediately becoming a little bit difficult in these questions 1 and 2. And in the exam, even the exercises will fail because you come up with something completely new. I'm not gonna do this. Is there anyone here who can claim to draw, for example, question number 1? Just tell me where to start the ramp and towards where to proceed up to what, etc. Is there anybody here? You
Hocam
don't
önce
have to.
shift'i mi yapmamız lazım?
So how would you really solve the problems? Do you remember my trick from the previous trivial cases? Those are trivial, so I don't use the trick, but now I should use the trick. The trick is the following. Just give a value to the time and see what value it really corresponds to.
Hocam
Yep.
bölü 2'yi dağıtırım ben.
What I would do, since this ramp has 2 points, it's the starting of the ramp and the ending of the ramp. It may be a negative way of going to the ramp or a positive way. But whatever it is, it's the value, the value at 2 points is critical. So I would give, for example, t is equal to 0. Sorry, t is equal to 3 to this one. At t is equal to 3, minus 3 plus 3 over 2 is 0. So at 1, 2, and 3. At 3, what I really have is x of 0, which is this point. So I have this point. I mark it. And then I give 3, 2, 1. I give 1. T is equal to 1 to the first. And minus 1 plus 3 is 2. Over 2 is 1. So at 1, at this point, I get x of 1, which is this point. So here's the answer to the first part. Okay. Each student may have his or her own way of solving such questions. Some of you said, first I distribute to the scale. So I convert this to this form or this to this form. You may find equivalent forms of writing the same thing, and then first apply one of the things. I don't know, God knows what, maybe the shift or the scale, I don't know. But for example, for this one, it seems to be first folded, okay, and then shifted by 3 to come to this point, and then extended. But I'm not sure about that. Okay, you may develop your own.
Hocam 0 neden verilmedi peki t'ye? T'ye 0 verseydik
Okay, let's give t is equal to 0. Let's do that. I didn't do that because I know that when I give t is equal to 0 here, it is x of 3 over 2, which is x of 1.5, which is somewhere here. It doesn't have, the function does not have any value at 1.5. It is 0, and it doesn't correspond to any shape discriminating point. So that's why I didn't give t is equal to 0. I was trying to get something from this minus t plus 3 over 2, a value between 0 and 1. In fact, the values at 0 and 1. So for 0, t must be 3. For 1, t must be 1. Only then I have x of 0 and x of 1, which I can mark clearly, like this point and this point, here and here. And I just interpolated in between because there was a line in the original. Right? Okay, now let's move further. For today, the last thing that I want to talk about, this is technically an important issue. Okay, so pay attention to this, is periodicity. A periodic signal for continuous time makes sure that x of t is equal to x of t plus the period, which is also equal to x of t plus any integer times the period. So if something is periodic with, let's say, 5, it's also automatically periodic with multiples of 5, like 10, 15, 20, etc. For all t element of real numbers and for all k element of integers. Okay, this is the definition of periodicity for a continuous time signal. And it immediately shows us that any signal which starts at some point and or ends at another point is not periodic. So, for example, the signal which was 0 up to this point, and then a sinusoid starts and goes on along T. Is this a periodic signal or not?
Yes.
Yes. Another answer, maybe, from another. Do you agree?
Değil
Cihan Berk
herhalde.
says not. Okay. Yeah, no, it's not periodic. Because when you shift it, as you see, it becomes maybe something like this. Even if you may shift by one period to the left, these two are not equal. Can't be periodic. The rectangle shapes or the ramp or triangle shapes the signal is always in. Am I disconnected? I hope not. Okay. So sines and cosines are periodic. Example, x of t is equal to cosine. Let's give a number here. Cosine a times t. Okay, a is a real number. This is periodic. The question is, what is the period? If it is periodic, you have to answer this. What is the period? Conversely, the reciprocal or the 2 pi reciprocal version of it is, what is the frequency? The first thing that you have to be aware is that a period times frequency is equal to 2 pi, because we are using radians. And therefore, the frequency unit is radians per second, and period unit is seconds. So frequency is not 1 over seconds. It is radians over seconds. So their multiplication gives you 2 pi. This is the notation that we will continue to use throughout the sinusoids that we will investigate. Here, for the radian notation, an angle of 0 is 0. An angle of pi over 2 is 90 degrees, but it's not 90, it is pi over 2. An angle of pi is 180 degrees, and an angle of 2 pi finishes the whole circle. 2 pi is 360 degrees, okay? But it will be 2 pi. So let's come back to the question. The frequency from here, frequency is equal to A immediately, and period is equal to 2 pi over a. Let me give a more solid example for this one. Cosine 2 pi over 8 times t. So the frequency is 2 pi over 8, and period is 8. So anything as a denominator of 2 pi here is actually the period that you have. Some other questions before we stop this particular course is what is the period of this signal x of t is equal to 2 times cosine 2 pi over 6 t minus pi minus 3 sine 2 pi over 5 t plus 1. As you see, immediately I'm extending the difficulty of the question by some orders of magnitude, 10 times more difficult. What is the period? You may find one of it is 2 over capital until the next week, where we will meet at the same. Maybe it was a little bit, yeah, there was a raising hand.
Hocam sesiniz bir süre kesildi de ne dediğiniz hakkında hiçbir fikrimiz yok yani şu an.
I see. What I was saying is that this question was difficult, if you can hear me now. I didn't say much. This new question is now difficult because it's consisting of shifted versions of two periodic signals. These things don't contribute they don't contribute to the period or the frequency. Okay, you can ignore them for finding the period. We have two periods. One is 6, the other one is 5. Two periods, and their combined period is the least common multiple of the following, which is 6 times 5, which is 30. So this is the period of this x of t, and the frequency is equal to 2 pi over 30, which is pi over 15. These are the period and the frequency. In another example, if this is 4, then t is the least common multiple of 6 and 4, which is not 6 times 4, 24. It's not, because 12 is 2 times 6, which is an integer multiple of 6, as well as 12 is 3 times 4, which is an integer multiple of the second period. Therefore, the actual period is 12 for this one. and the frequency is 2 pi over 12 or pi over 6. As you see, we ignored the shifts. We don't care about the shifts for evaluating the period. We are only looking at the periods of the components. If you have two such components, this is how to proceed. If you have three periodic signals, you have to add them up. And by the way, these scales are also irrelevant. 2 times cosine or minus 3 times sine. I'm just writing them to confuse you. They don't contribute to the period. And then I'm asking you the period. The period is the least common multiple of 6 and 5, or 6 and 4, as I have indicated. Okay. The period for discrete time signals are indefinitely more difficult, so we have to leave it to next week's lecture, and we'll stop at this point. Could you follow my final words? Because at some point the internet was unstable, as you suggested. So why is it 12, you say? It is the least multiple. Normally, the least common multiple could be the multiple of those two. But 6 times 4 is 24, and before 24, there is another period where they meet. For example, we have, this is, let's say, from 0 to 6, which is a period of the signal, and the other one is up to 4. So this is one signal, and this is the other signal. At which point along the real axis do they meet again? This point meets again. At 4, it repeats. At 8, it repeats. At 12, it repeats. You come to the same point. And for 6, for the signal with a period of 6, you go to 6, you in one cycle, you come back to the original signal, and then you go 6 again, and you come back to the same point. So this point is exactly repeated at this point, and the period is 12. That is known as the least common multiple. For the least common multiple, you have to first eliminate the shared multiples of 6 and 4. What is that? It's 2. Let's divide both 6 and 4 by 2. Then you get 3 and 2. And then where do they meet is the thing that you may be looking for. Actually, this is something that you have to work out if you don't understand why 12 is the period of interest. Because in the question, if you say that the period is 24, that is technically incorrect, because a period is the smallest period of the signal. 24 is also a period, but any integer multiple of 12 is a period, but the real period is the smallest among these, which is 12. Okay, so you have to find or devise the methodology to find the least common multiple, which is 12. If one sinusoid is, or one signal is periodic with 6, and the second one is periodic with 4, the period is 12. Okay. All right. It may be time to make a stop. The internet may become unstable again. Before that, let's stop it, and we will meet again on Monday, next Monday, in the same address. I will indicate in Canvas. I will try to indicate, but even if I forget, this is the address that you must always click to, and we will do our classes here. If you may have questions, you may ask again now. Or there is an open discussion forum for the first week. You can write something on the discussion forum, where your discussion regarding your projects is also very critical. So do not forget to write something over there.
Hocam bir soru sorabilir miyim?
Yes.
Hocam kosinüsteki t'nin başındaki katsayı açısal hızı mı veriyor yoksa frekansı mı veriyor?
Which you're talking about? This 2 pi over 6 of cosine.
Evet hocam. O açısal
That is
hız
the
değil mi?
angular frequency. Hı hı.
Evet,
That's the angular frequency.
Tamam, teşekkürler.
It's not the frequency in terms of hertz, which is 1/seconds. Frequency, angular frequency and frequency are both the same, but if you write the frequency in terms of hertz, which is 1/period, that would be hertz. If you say 2 pi over the period, it's the angular frequency, which is radians per second.
Anladım hocam, teşekkür ederim. Sağ olun.
Okay. When will we do the upload of the recordings? The first day, Monday recordings did not have my picture, which you can see in the recordings. But today I found a way to record both my visual and the screen all together, hopefully. So I started doing it that way. Nevertheless, I am collecting the recordings. And they will, I'm still working on a way to publish them at some means, by some means, preferably YouTube. But before that, if you're curious about these, you may go back to the Facebook page and scroll down and look at the older recordings, which are also very nice. And they do the same thing. I do the same thing over there. So you may also watch those in case you don't understand from here, because there is an instability in the internet speed. It may be even better in the previous videos where there is no internet thing. Okay, they were just analog face-to-face communication recordings. So I would advise that one. So until next week then, take care. We will meet at 9 o'clock on Monday again. I'm now stopping the recording.